Now, you've had grounds in laboratories, right? It's usually set to zero potential of any measurements in a chassis or basically on a signal ground. We'll talk about earth grounds, but we're going to talk about one or two problems. Yeah.
Before we get into grounds, could you show how you did LV on the quiz? 2A goes with the Bode plot.
What does it look like? This right here, this is frequency, so this is going to be 1 over 2 pi square root of LC. Now this is a resistor, so L there is the lead inductance. This breakpoint right here is going to be 1 over 2 pi R times C. From this one, you know R, so it's 10,000 ohms, right? From that, you know this frequency. What was the frequency?
10 megahertz.
So it's 10 megahertz. Now look, it's really as straightforward as I showed you. You got 10 to the 7th is equal to 1 over 2 pi. That's 10 to the 4th, right? Times C. So we can get C directly from inversion here. So we get C is equal to 1 over 2 pi, and it's going to be 10 to the 4th times 10 to the 7th. And that should be the answer. 1.59 times 10 to the minus 12 farads. Now, this frequency was at 2 gigahertz. Now you're going to go ahead and say 1 over 2 pi square root of LC is equal to 2 times 10 to the 9th. I'm going to go ahead and invert this, so I have 2 pi square root of LC. It's going to be 1 over 2 times 10 to the 9th. So I get 1 over, and this would be 4 pi times 10 to the 9th is equal to the square root of LC. So if I square it, I get LC, and that means I get L as 1 over 4 pi times 10 to the 9th squared, and then it's divided by 1 over C, and C is 1.59 times 10 to the minus 12, and that should be the right answer. What is the answer for that?
3.98 nanometer.
It's just get C from the low one, you get L from the mid for the resonant frequency, and always, anytime you see a resonance, like either a V or a notch like that, the resonant frequency is always going to be 1 over 2 pi square root of LC. Well, getting back to grounds, I'm going to just show you the 3 type of grounds you typically encounter. And grounds, a lot of times in EMC work, we're not dealing with usually high power applications, so it's a different type of problem than real power problems. You know, when you're dealing with power, you're dealing with extraordinarily large currents and powers and trying to really conduct power from one area to another, or communicate it, I guess would be the word. And the problem with grounding usually has to do with safety and lightning. These are different types of problems. Lightning is a real problem. That's a lot of times has a lot to do with the electrical codes that are required. But for grounds, this is in the book, and it's a very, very brief overview, just to make you familiar with it. The first ground you see is this. That's called a signal ground. Now, a signal ground, what do I mean by that? Well, in your first laboratory work, they may have a breadboard, a simple breadboard, and there they're going to say ground. That's the symbol for ground, and it technically means 0 volts with respect to measurements. So typically, if you have a meter, you would put the negative lead there, that would be the ground, and as you go around and measure points in the circuit, all voltages are with respect to the ground. That's a signal ground. It's the first thing you should have seen. You should be familiar with that symbol right there. It's just 3 little dashes that are progressively shorter. The next one is the chassis ground. The chassis ground is this. And a good question is, what do you mean by a chassis? Almost all electronic equipment up till very recently was mounted in a thin steel or aluminum frame, like a box. And that would have that box, say you have a box like this, that box will have a ground on it, right there. And it's called the chassis ground. So the entire chassis has that, and that's 0 potential, 0 volts. Now, if you have chips and other things, and they have a wire from there to, say, a chip here, on this chip, we'd have a signal ground. There are power supplies, there are a whole bunch of other things that complicate this. There'll be positive leads, all this stuff going into each thing. But this wire right here will have current in it if the signal ground and the chassis ground aren't the same. And it can be significant at high frequencies because there will also be an inductance there where you'll get millivolts of difference and actually the chassis and signal ground, sometimes even more, maybe tens of millivolts at higher frequencies. The problem with that is when you're doing measurements or you're trying to do amplification of like an incoming signal from an antenna, and it's got a very small signal you're trying to amplify. This right here may have such a significance that if you're feeding the antenna's input into this, that difference right there will cause, remember, anytime you have a voltage potential, you have a capacitance, right? Anytime you have a capacitance, there is going to be mutual inductance and mutual capacitance between these 2 points. And if this, say, you got a high frequency oscillator on there at 2 gigahertz, that 2 gigahertz, wherever it might be, might bleed into that, and it'll cause the problem. So trust me in this. Did you ever do laboratories where you have to measure things and you see noise? Usually you get a spectral analyzer and you see where the noise is, what frequencies. And it's usually at single frequencies. If you get wideband noise, that's a totally different kind of problem. It's the way you actually analyze something. If you just have time domain, you see it doesn't tell you anything. You take that and you do fast Fourier transforms on that with a spectral analyzer, and you'll see the frequencies, and they're usually very up. 60 hertz is the dominant one, a very low frequency you got to get rid of. Then as you go up in frequency, if you have oscillators, a lot of times you'll see, well, you will see the fundamental for clock frequency. If you got 2 gigahertz clocks on there, you'll see that, but it's usually the higher frequency components, the rise times of that, you'll really see. That's the chassis ground. Now the ground that electricians and anybody that's in the power industry is most aware and concerned about is this one. This is the earth ground. That's the symbol for it. How many have seen these grounding rods that you get from Lowe's or Home Depot? All right, they're usually about yay thick, about 3/8 of an inch to a 1/2 inch thick. I don't remember exactly. They're solid, and they're usually alloyed, so they don't rust or anything. And they're fairly stout. You can bend them, and I did bend. We did have to bend them. We made what's called a chicken stick when we had this railgun project. We had these capacitor banks that would charge up to 10,000 volts, but they were like 33 millihenry. That is an enormous amount of energy, 1/2 CV squared. You're talking about a phenomenal amount of energy in there. You want to make absolutely sure that these things are discharged. If you grab them, you can kill yourself. So we took a grounding rod, one of those, and we bent the tip into a hook. And then we took that rod and we used, I think it was 4-aught wire, it might have been 2-aught wire, and we had this hooked to the actual earth ground of the thing, of our building over there. And so when we wanted to discharge them, now this is one of those things, you can't just put it across there and get a huge amount of current. So in series with all this, and it was right after the chicken sticks connection between the 4-aught and the big thick ground rod, we had something called a water resistor. Do you know what this is? You know that big like surgical tube? It's really a very thick plastic tubing about this thick. This is the radius, the inner radius. It's a good 1/4 inch thick plastic. You can see through it. What we did is we got corks, and you have to put you have to drive a small wire, thin wire through the entire corked area. You with me? So if you think about this is a water resistor. This is something that actually may be of benefit to some of you. So it's a thick thing like that. And what you do is you're going to put a real thin wire between the two. That wire you have to take a needle or something and drive it through a cork. So the cork's here, you put the cork in it, and you put the cork down here. But before you actually put the second cork in, the top cork, you fill this thing with sand. This is called a high voltage fuse. If you ever have to deal with real high voltages and you want a fuse that will prevent, there's a way to get this. The copper wire we chose had a certain value where it's an I squared times time. I forgot what they call that, but it has to do with the stiff current parameter. So it'll blow at a certain rate. You know how fuses are rated like 10 amps and all this stuff? There's a certain amount of time before they blow at 10 amps. Anyway, this thing was going to blow, I don't remember what it was, it went over like 10 amps or something, we calculated this. But we fill it with sand. The reason we do, as soon as this wire blows, we want the sand to collapse on it so there won't be an actual arc between the 2 points. If there's an arc, the current will be sustained. That's why you can't have a high voltage fuse with just a thin wire. Even though that wire may sever its ionized region, and it'll continue the current, just like a lightning bolt. So we filled it with sand, and then we hooked it to ground. Now, Sorry, this is the high voltage fuse. Now the water resistor goes, so you got basically a chicken stick like this. Then this thing is going to be attached to the high voltage fuse. Then you have your water resistor. So this is the water resistor. This fuse and this thing are basically made in a very similar fashion. So what you end up doing is you're going to have this cap, and you're going to have water, and then you have copper sulfate. Copper sulfate. And the reason we put copper sulfate, or we could use rock salt, is so it can conduct, but it's going to have a certain level of conductivity that would limit the current at 10,000 volts to be less than 10 amps. Are you with me on this? Much less. Now this water takes a lot to heat up. So it's maybe this long and that thick. After you discharge these things, there won't be an arc, there won't be a bang or anything like that because it's limited by the water resistor. But if you feel this water resistor, it's hot. I mean, not hot, but warm. You know it's up. It's definitely a lot warmer than it was. And that's where the energy is dissipated. It's called a water resistor. I'm telling you this because some of you will be working at companies where people, small companies especially, don't really know all this and they find out the hard way. And usually the hard way is destructive testing where you're going to lose some money. This is the thing you need to do. Water resistor and high voltage fuse in series with a solid thing. Because when we discharge these things, there's an insulator here. You have to take it and put it on the capacitor, on the anode of each and make sure it was discharged. Because you can kill yourself with these things. You don't realize it until you're around it. That was my experience with high voltage fuses and stuff like this, and also the earth ground. So the earth ground is critical for something like this, because frankly, if worst case scenario, you ever get a live arc and it goes over this 10,000 volts, might be able to do it if you have a thin, and it goes over this and over the water resistor. If you're not in the earth ground, God knows what may happen. You can start fires, who knows what. When we fired that railgun the first time, I'm just telling you some things that happened at Shock. We had these really thick cables that we used. They were heavy and they were insulated cables that were running around that coupled the power to the gun, the actual capacitor output to the railgun, and we had something called an ignitron. It's a high voltage switch, and I'm not going to go there now. When we shot it the first time, these things are jumping. And there were arcs out of the wall outlets. It was a nightmare. I mean, I thought I knew it. I thought we had done a fair job preventing any kind of problem. I learned about EMC hard way there. There's a lot more to this, but I got very interested in electromagnetic compatibility and interference there, and I learned a lot of things that they don't teach. Remember, the railgun had a current of up to 400 kiloamps peak. It was just a real fast shot. Most of the time it was limited to like 40 kiloamps. I don't think we did a lot of shots much higher than that, but that's a lot. And it's a very short rise time. So here's the thing about grounds that you can take from this. That little aside there is something based on personal experience that somebody may be helped by at some point. You know what a transformer is, right? So suppose I have a long wire. This is going to be the easiest thing. And I have a current I. And let I be a function of T. I naught, just say it's cosine of omega naught T. Doesn't matter what it is, this is a current. Now I have a single loop like this, and the loop has an area A, and I'm going to break a point here, and I want to know the induced voltage here. First you have to know A, then you have to know B, and then you have to know the length. Now there's only one turn here, right? Well, the way you always do it, if you have I, you get H or B. I'm going to go ahead and get B. So B up here if the current's going down that way, be coming out of the board, right? And B, as a function of T, would be equal to mu 0, we'll assume it's air fill. It's going to be times I of T over 2 pi rho. Let's measure this distance as rho. In the A phi direction, this is just perpendicular to the board. And if we integrate that over the entire area, we get the magnetic. So if I integrate B of T, and I'll put it A phi, not in a differential surface, and if this is dz, or if this is the z direction, and this is the rho direction, this is going to have an A phi component because it's perpendicular to the board, and then it's going to be d rho, dz. Let's say z goes from 0 to L, and rho goes from A to B. And you can see the total flux there is going to be mu 0, and it's going to be I of T over 2 pi, then it's times L, that's the length, and then it's going to be times the natural log And that would be the total magnetic flux here. So the voltage, if that's the flux, you know the EMF, induced voltage, or the voltage, call it V of t in magnitude only, I don't care about polarity. There's going to be a time derivative of that, and that's equal to mu 0 L over 2 pi times the natural log of V over A. That's times di dt. And what this really is going to be the mutual inductance. It's going to be times di dt. That's the voltage. All right, now I said all that to say this. I didn't even bother taking the derivative of this because, you know, the derivative of this is going to bring out an omega naught. It's going to be minus sign. It's going to be minus omega naught sine of cosine omega t. Just take a time derivative. That's a voltage, right? If there's an opening there, that's a voltage right there. But if there's not, then there's a resistance in this loop, and that resistance would limit the current to that induced voltage that would be distributed around the loop. So you get a current I. That's my point of this. Now here's the thing with grounds. This is where it applies. If you have a closed loop, and any kind of high currents near there, time-varying currents, you get an induced ground loop current that can be a real problem. So if you have a system, and this is something where we're going to talk about either signal to chassis or chassis to earth ground, it doesn't matter. But if you have a system here, and you got a chassis, so I got a chassis ground here, and that is probably going to have other things attached to it, but then ultimately there'll be other things, other circuits and stuff like this that are going to come here. All this is going to be attached to an earth ground. If I do something like this, I'm trying to show you this, there are usually many, many things. You got a chassis ground here, chassis ground for that. But if you have more than one connection to the earth, let's put another one here. I don't know what the area is, but can you see right here, we have a path, goes there, goes in through the chassis ground, come over here, into the chassis ground, back here. And what you end up having right here is something where you can get a ground loop easily. And what happens is it doesn't even go around there, it does this. Current goes up and then back down there. And that's the dangerous thing with any time you have grounds. In Dr. Wentworth's book, he'll show you a thing about grounds in chapter 9. There's so much more to this. In EMC, we go into detail about this. And with compatibility design facts. This is on page 522. He'll show you proper grounds and improper, and he'll show you that 2-point ground, and that is a real dangerous thing to do. Where you put it on either side of either of a chassis like that, and because you got a ground loop, you also have things of currents flowing in the ground. It'll flow up through the ground in your device and down. So if you look at the bottom page 522, he'll show you that. He talks about some other things with grounds. Single point grounds are the way to go. Typically, there are exceptions, but usually at that point there are tricks that he doesn't cover in the book about how to prevent problems. Grounding is a real problem. You all know with washers and dryers, all that, they have something called a single fault indicator, a ground fault indicator. And do you know why that's there? So typically, when you have a wall plug, there is a plus and a minus, right? Now, as long as the current that's coming out of the plus is returning to the negative, it's operating fine, right? But that plus right there will also drive down to the earth, they'll drive current to the earth ground. This negative point has something, it is referenced to ground. Do you follow me? So if I'm grabbing a washing machine and say the negative return line gets broken off for some reason, and I'm grabbing it, that current will try to go through me to the ground. It can kill me if it's high enough voltage. Typically, no, but you get a heck of a whack. If you're like standing in a salt water solution and you grab it with a very salty hand, you might get knocked out and die. But that would be for a 240, I mean, when you get plus or minus 120, it'd be hard to do that, but it's possible at least. So what they do is this, they have a ground fault indicator. And if the current going through here is not the same as the current in there, it trips. So there's a ground here. In the minute this current is not equal to that current in magnitude, the breaker trips. That's the ground fault breaker. And that's the thing you be thankful for. Now, the old days, they would have a fuse. You can't reset these. These are resettable. Anytime there's water in a bathroom or in a kitchen, or anytime there's water, all the outlets have to have a ground fault. They have to be on a breaker that's ground fault according to code.
So would you need something like this, is like a saltwater pool or something? Also, just
For grounds?
Yeah,
We're indoor or outdoor?
outdoor.
Depends on the size. What kind of size?
I was just assuming like any, like at the beach or something where there's a lot of salt on the ground.
Whoa,
water.
hold on. A pool that has electrical
Not
outlets.
inside the pool, I mean around the pool.
Yeah, but anything that is near water, it doesn't matter if it's fresh or salt. If it's an electrical ground, I mean an AC electrical ground from Alabama Power, power's coming in like that, it has to have a ground fault breaker. Has to. Anytime there's anything, because here's the problem with water. You're flicking the water, and all of a sudden you're going to be grabbing something. You can easily become off of, I mean, how many people have got zapped in some way, shape, or form by electrical equipment? I have been zapped more times than I care to think about. Guess what? You became the conducting path because you are, for some reason, the conducting path, and there are a lot of reasons for that. This is something you're responsible for. All right, this is called common mode choke. It's a very, very useful device. You can wind them yourself. It'll save you many, many problems. And there's a lot more to this. We get into this more in the compatibility course, but you'll get this in some of your design courses. So what is a common mode choke? Ultimately, it's simply a transformer. This is the electrical symbol for it, where you get a dot there and a dot there that indicate the polarity. If you've had gross for power, you know this one. There's going to be some current I1 here. It'll generate some voltage V1. There's also a mutual inductance here. Then there's going to be a V2 here, and there's going to be a current I2 here. Now we're just looking at these in isolation, but I want to show you the actual physicals, what a common mode choke looks like. If you take a toroid, and it has a cross section that typically is just circular. This would be area. I mean, it's basically a donut. What they'll do is they'll take one wire, and we wind them ourselves, and you're going to have so many turns. This is going to be where I1 goes, and then you're going to have another wire. So this would be I2. And here's how you get the dots on them. So the way you do it is, what if they're just straight bar, not wound? And you put a bunch of loops there, like such, and I get I1 in here. Well, which way is the magnetic flux going in the center of this bar? You got a right hand. Put your right hand, put your thumb in the direction of current, and your fingers will curl in the direction on your right hand of the flux. Now, if you're outside, it's going down. If it's inside that bar, it's going up from the way I drew it. So this is the flux. So that's the magnetic flux from the first one. Then do another set. Now put a dot on this one. Another set. Now, if you put a current here, I2, which way is the flux? I wound them in the same sense. That flux is going in this direction as well. Therefore, you put the dot here. So if you have two coils of wire and you put the current in the one with the dot and it's going in one direction, you put the current in the other with the dot and it's going in the same direction, you leave the dot there. If, for whatever reason, the flux is going in the opposite direction, in other words, it's wound the opposite way, you just take the dot from there and put it down here. That's it. It's called a polarity of the transformer. It's really a magnetic circuit. It's not a transformer in the true sense. Now there's a mutual inductance and there's a self-inductance. And I'm just going to assume the self-inductance is the same. So we have the same number of turns on both. What happens when you have these things? And here's what I'm going to do. I'm using this model. And I'm just going to show you what happens for both common and differential mode. And I'll explain this. So we're going to start by defining what common mode is and defining differential. Now I1 is a current here, and it's composed of I common, and that means I common is nothing more than the current that would have the same amount here as here is called a common mode current. Then it's going to be plus a differential current. Now down here, I2 is equal to I common minus I differential. This is how we actually figure out how much is common mode, how much is differential. And I'll give you a clear example. I'm going to say I1 is equal to 5 amps and I2 is equal to 1 amp. If I add them up, add I1 and I2, that's 2 times I common. Do y'all see this? If you add that to this, you get 2 I common. So if I want I common, that's it. You add them up, divide by 2. It should make sense. How do you get I differential? You take what? I1 minus I2 and divide by 2. You take I1 by I2. And I common's dead, and you get 2 ID, right? So ID, we take that and divide by 2. So what is it for this one? Well, I've got 5 and 1 is 6. 6 divided by 2. I common would be 6 divided by 2 or 3 amps, right? What's I differential, guys? Well, it'd be I15 minus I21 is 4. 4 divided by 2 is 2 amps, right? Now what we have to do is see how this particular common mode choke responds to either common or differential modes. It's in the book, it's very simple. So we're going to start with common mode. I'm going to do one of these. Here's I common coming in here. Here's I common coming in here. Here's the dot, here's the dot, here's M. Here's L, here's L. This is plus minus V1. This is plus minus V2. And what we're going to do is assume we're in the phasor domain at a constant frequency. Now, normally the voltage across an inductor is just J omega L times the current. But if we have a magnetically coupled circuit, like we do here, the voltage V1 is going to be J omega L, that's called the self-inductance, times I1, but in this case it's I common. But then it's going to be plus J omega M, and that's the mutual inductance times the second one, which is going to be I common. In general, it's this one. If you have any device that has a mutual inductance, another current, I'll put this down for you. This is L, L, and M. If you have an I1 here and I2, now you'll notice they both have to be going into the dotted terminal. Then what you get is this voltage here, V1, will be equal to J omega L times I1, but then it's going to be plus J omega M times I2. If I2 is going in the other direction, that becomes a minus. And that's the key to this whole thing. Okay, so that's V1. V2 will be identical because it's common mode. V2 will just be J omega, and then it's going to be M times I common plus J omega L times I common. Usually this is I1, I2, but they're common mode. So if you look at this, V1 over, and I'll call this IC, would be the inductant. If you look at this, that's the voltage, the current is IC, right? So the apparent impedance of this, V over IC, looks like J omega L plus M. And that's the key to this. If you are worried about the effect or the actual impedance of these things for common mode currents, what you can do is simply take this inductor, get rid of this M, this is just for common modes, and you can replace this inductor by the value L plus M here and L plus M here. Usually L is about M, very close to it.
Would you mind saying what M is again?
The mutual inductance. It'll be given. You can calculate it for a lot of things, but I'm not going to ask you to do that for this kind of problem. So the self-inductance is given mutual inductance, but remember this is for a common mode choke. So on purpose, you try to put the windings, have as tight a space, have these things spaced as small difference as possible, to as many turns as you need, but the more spacing there is between them, the more the mutual and the common, or I should say the mutual and the self-inductance are different. This is an important fact. So this is the equivalent, which means what? If we're talking about differential currents, right? I'm sorry, common mode currents. Common mode currents, where you're going like this. You can see the impedance here, and this is the current you don't want. It's really going to be J omega times L plus M on this side, J omega plus times L plus M on this side. Now, the reason this is so important, because when you have devices and lightning hits, lightning runs through in a common mode fashion through the wiring, and lightning is a nightmare. And so for ground loops, there's problems with that too. You want to eliminate common mode currents as much as possible. You only want differential. So if it's going to eliminate, the impedance of this would be J omega times this. That can be huge. If you're talking about frequencies of like 10 or 12 megahertz or even gigahertz, that impedance can be huge and it can block a lot of the common mode current. That's what you want. Now when we do differential mode, this is in the book. If you're going to block common mode, you want to allow differential mode, because that's the way things work, right? When you have an extension cord, current goes down one leg, returns on the other wire, right? Same magnitude, opposite direction. You want to allow that. So if you look at the differential mode, and this is going to be, remember, I1 is now going to be ID, And I2 here is going to be minus I differential. What this will actually look like. Here's ID going this way. Here's ID going this way. And here's my voltage, I'll call it V1. And of course we have L, there's a dot, and here's M. So what is this V1? Well, V1, as before, will be J omega L times this current ID. Then, because the current's going the opposite direction coming out of the dot, it's going to be minus J omega M times ID. And if you look at that, if we take V1 over ID, which is the effective impedance of a single coil, now what do you get? J omega, and now it's going to be L minus M, which means the closer L gets to M, the less impedance that has. And ideally, they're within 1%, maybe even less than that. So it doesn't block differential current. It'll block common mode. This is especially important when you're dealing with any kind of wiring that could have either a ground loop induced in it, like, you know, whenever you get coax cable running all over the place, you know what I'm talking about, right? You get huge lightning strikes nearby, it'll induce in the magnetic field that's very large in there that will cause a ground loop if possible, it usually does. And if you don't have a common mode choke, you got a problem, because that current will go in through the coax into your whatever, your router or your TV or whatever you have, unless you have some sort of block. And there's lightning protection devices, and usually they have it so if the voltage gets too high, it'll short to ground, something will open up. So it means ultimately, this is what I'm after right here, I can replace those coils if it is differential mode, where you have ID here and ID here, by just simply J omega L minus M. Now, if you're looking, and this is an important part of this, the effect of the filter on the overall operation of the circuit you have to take into account. You're going to have some load here. Now, if you look at this, right here, this is going to have J omega L minus M. Can you see that the total amount of impedance in this circuit is going to be RL plus 2 J omega L minus M. If 2 times J omega, 2 times, I'll just put magnitude of J omega L minus M is much less than RL, your circuit is going to be unaffected by that common mode choke. Here's the thing that happens with this stuff, and I'm trying to give you an idea of why this is so important. Dr. Wentworth's book basically just, he's covering so many topics there. He just throws this out here. You should be aware of this. It's very, very good to use a common mode choke, especially, you ever get that 60 hertz hum on anything? If you have, especially older devices with audio amplifiers, if you have long cable in here, it's a 60 hertz hum you can hear. While common mode choke, if you put it in series with, once you get past the plug level and into the input, you have to get this at the input of your devices where it has it goes from AC to DC after the full wave. You put that in there, it gets rid of the heartbeat. I said something here where you really probably don't appreciate it yet, but you will in time if you ever have to do this kind of stuff. So here's why it's so important. Let's assume I have wires here, long wires, and they're going in and they're feeding something, coming in here, and it's going to feed some devices. Here's my chassis. Wire comes in here, in here. If you have common mode current, especially really large currents, this current goes in there, it's going to flow, and it's trying to get to the earth ground or chassis or earth ground, and it's going to go through your circuit whatever way it can find, path of least resistance, usually through things like differential amplifier inputs, and destroy them. This current's also coming, all this current piles up and it's going to get into that ground lead, and anything between this input and here, that's a short circuit path, is going to get pulverized by that. And basically it'll cause problems. This is meant to be a differential kind of circuit. So usually there's a transformer or something here, there's a transformer here, and then on the other side, it'll go right through that transformer, short it out, go to ground, it'll destroy the thing. Has anybody ever seen the aftermath of what happens to lightning? A device that's around a direct strike of lightning? It's a disaster. Or ground loops. Ground loops are not as bad as lightning. I've been around some of that. Now we're jumping into the section in chapter 10 on microwave. So microwave, what is When somebody says microwave, what are the frequency ranges you're thinking? Wavelength very small, i.e. micro, but frequencies of the order of a gigahertz or higher. Now, you can argue that point, but typically a gigahertz or higher. The reason they talk about that is because microwave is really something that's used. There's a transition from coax cable in the hundreds of megahertz range to waveguide from microwave or planar lines because they're frankly more efficient. There's less loss. When we talk about microwave circuits of interest, we're not talking about waveguides. Those would be things that connect to it. We're talking about something that's built on a board where you can have a link that can communicate information from one chip to another, microwave information. And the path is usually greater than a tenth of a wavelength, significantly greater. So you can't just assume, copper wire is copper wire. It now looks like a transmission line or a waveguide or both. So here's what typically happens. You're going to have something, and it's called Doroid board, or it's a high frequency laminate. You don't have to worry about this, but this is copper cladded board. Sometimes it's only a single layer copper. Do you know what FR4 board is, the green board? If you ever rip apart routers, stuff like this, low frequency routers, you'll see a green kind of a board with all sorts, it looks like a whole bunch of things soldered on the back of it. That's called FR4 board. That's very lossy. You can use it, but not at high frequencies. Usually they use something called Doroid board that's a high frequency laminate. And what it is this, and the reason they use it is because there's lower losses. It's a simple board where you have copper on top, and the copper is very thin. So you're going to have copper here, then you're going to have a dielectric between it. Just assume the top has copper on it. Then you're going to have a bottom. This is going to have a certain thickness, call it T. It's going to have a certain area A. And this thing does have a thickness, these layers of copper. And they'll be down here. So this is when you have basically copper on top, copper on the bottom, and then this is going to be high frequency Doroid board, typically. Now this Doroid board will have a certain value of epsilon relative, and it'll be very low loss. For all intents and purposes, you can forget about the loss. Epsilon relative 2.2 or something like this. Now here's what they do with that. When they mount components on it, they know where they want to mount components, and they want to run lines between here and here, say here and here, and maybe here and here. So what they'll do is they'll mask these things with a photoresist, or actually it's just going to be a resist, and then they put it in a solution, and they get rid of all the copper except the connecting. VLSI technology. You know how, you can develop it with electron microscope. You can use an electron beam or anything like this, but here's the deal. You know how a camera works, right? An old camera. What you had is something was filmed, and when you exposed it to light, the film became developed, and then you took it to someplace and they washed that stuff, and the more developed it was, the more material came off, so it looked lighter. This is how pictures were back in the day. Polaroids and stuff like this. So a photoresist is something where they put something on there, and what they'll do is they'll leave the photoresist everywhere they want the copper, and then everywhere they don't want the copper, they develop it. They put either light, something like that. They can use an electron beam, it doesn't matter. So they'll be left with, if you're looking top down at it, if this is the actual copper layer that was, at the end of the day, after they put the photoresist down and they develop everything but what they want, you're going to be left with copper like here, 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 and these are just electrical connectors with a certain width and a certain thickness. So let's just look at one of these little paths from the side. And here's what it will look like. This is the thickness of the Doroid board. Here's going to be like the copper line. The copper line will have a width W, and it'll have a height. I think he does it this way. He calls this the thickness T and this H. Here's really what it is. Now remember, there's copper back here too. The whole back of that thing's copper. What this is a transmission line. Between here and here is a plus-minus conducting path. Are you with me? And it looks like a transmission line. Not a coax cable, but it looks like a transmission line where the top has there's a certain width here, and then there's that dielectric. And then down here, this is all copper. And effectively, there's a capacitance between them, and there's going to be a series inductance with these things. So it is a transmission line, is what I'm going to get at. Those transmission lines that you create, they're called microstrips. The line that I'm trying to show you right here is termed a microstrip. And they are transmission lines, they will support DC because this conductor and this conductor have no way of shorting out directly. Unlike a waveguide, if you try to put DC on a waveguide, it just goes right across. I mean, a rectangular guide, it shorts it right out. Now, there's an upper operating frequency on this, and then it will look like a waveguide. And you don't want to go there because the minute it starts looking like a waveguide, you got more problems than you think of. You're going to have all sorts of other modes and a lot of losses. But this is the thing about building stuff for microwave engineering. In his book, Dr. Whitworth, this is in chapter 10, he discusses this and he talks about microstrips. He gives a great drawing on page 543. He's going to show you what I try to show you as a cutout version. And remember, the key thing about these right here is the value of epsilon relative. Now, the thickness and height and width will give you the characteristic impedance. I'm not going to test you on the characteristic impedance. There are tons of formulas for this on page 544 and 545, and I want you to know something. When you actually want this information, all the formulas he has in here, approximations, there are exact tools that you can use that are online there for you.
In my experience, if you have a controlled impedance line, and then you let the manufacturer know, and they'll like adjust it to whatever their.
But they can make the width, I should say this, if say we have a certain thickness board, H, right? And we want this impedance of this line, characteristic impedance to be a certain, it's based only on the width. You can adjust the width. Now, there are tricks on this one because I want to say one thing. As this gets closer and closer to the edge of the board right here, I did a journal paper on this years ago, and I don't want to talk about it right now, but it will change. So you try to keep them away. At least you want this height to be a safeguard for how close you get to the end of the board. If you get too close, you got a problem. It's not the characteristic impedance anymore that you want, and you'll get all sorts of reflections. There's a lot of stuff in there about calculating epsilon relative and xenon at page 545. There are tons of approximate formulas. Don't worry about that. Now I want to get into the real part that we need to, and that is, how do you do matching when you have microcircuits, microwave circuitry on Duroid boards? And I'll tell you why this particular technique is so important. You know, before what we do is, well, if you wanted to do matching, we a lot of times put either shunt stubs or series stubs. Well, a stub is long. When you have a very small amount of board to work with, that real estate is very valuable. You would like to mount things there. You don't want just a line going out. So what they'll do is they'll mount devices, typically capacitors, on the board that will impedance match what's coming into what's going out. So instead of having shunts in series and parallel, we're going to have real values. We start with our old friend Smith chart, but this is going to be a rotated Smith chart. Here's the equator, here's plus J, and here's minus J. Now that's a Smith chart. What I always try to do is show you the one circle. That's sort of my reference point. So this is R equal 1. This is the 0 point, and this is infinity. You got to know Smith charts to get through this course kind of deal. It's your go-to, your bread and butter. The difference between us and physicists, many times, are the techniques that we use to solve problems. And the Smith chart, as far as I know, is not used by physicists. Because this is specifically for design. It's not for analysis. There's a yield Smith chart, and here's the problem. I've got a certain load impedance, ZL. Remember, my microstrip has a characteristic impedance. So now I have a characteristic impedance of this line that I'm going to call Z0. And what I want to do is figure out how to put something between here and here that is either a capacitor or inductor that will perfectly match. Remember back in the day when you did this stuff, the first thing you always did is you found the normalized ZL, right? So how did you get it? You take ZL and you divide by Z0, right? That's the first step. There's another circle. It's on page 557. You've got something. This is the R equal 1 circle, and this is called a rotated circle. And this is the rotated circle. There are three possibilities for ZL. You can be inside the one circle, I'll call that possibility A. Or when you plot ZL, this would be ZL. ZL could be inside this rotated circle. It's just this circle folded on the other side. And this would be B. And then C could be outside of either circle. Now we come here and we're going to look at A. We're assuming ZL inside rotated circle. So if you look at this point, there's a real and imaginary point. The imaginary part goes like this, And the real part is gonna be a circle right here, right? And this could be like 2 plus J3, something like that. Now, no matter how much impedance I add or subtract from that point, I can't get this thing to the one circle. Remember, we want to end up there. Remember what the Colden rule of the Smith chart is. At the end of the day, all the matching will put you right here because that's a reflection coefficient of 0. So I can't, no matter what I do, I can't, if I add plus or minus J anything, I can't add a resistor. This just puts this around this trajectory, moves it there, right? If I put it. Inductor or capacitor in series, that's an impedance we're adding. So what I do is I go to the admittance domain. I take 1 over ZL. So this is going to be YL. It's simply 1 over the value of the normalized impedance. So if that's true, now we get YL, which is 1 over ZL. And it's at what's called the conjugate point. This length is that length, and it goes right through the dead center. Now, if you look at this, we're in the admittance domain, right? Admittances, you add in parallel, right? Not series. So we're going to add something here. And remember, we're normalized. Now, if I go up, this could have a value of like 0.2 minus J 0.01, something like this. But now there's going to be a trajectory. I'm not going to be very good at this, but if you look at the radius of that circle, the real part that goes through there, I can add a certain amount of J, or admittance, and I can end up here. So this is going to be 0.1, 0.2, and this is 0.3. So I'm going to add an admittance. That had a minus J. I'm going to add some plus JB here. But I've got to go from here to here. Now once I'm there, the beauty is, and that's the reason the second circle's right there. It's absolutely same radius, everything, just folding this. Now when I go back from the admittance domain to the impedance domain, so this is part 3, and go here, this will land on the one circle, 1 plus or minus J something. So this will be, must be 1, and it can be plus or minus. In this case, it's going to be 1 minus Jx, and I don't know what x is because we got to go from here to here. And again, this is just, the only thing you're doing is finding the value right there of the admittance at this point and taking 1 over that to get here. And the first value you're going to get is approximately 1 every time, has to be. Now to get rid of that, the only thing I do is add a plus J, right? Plus Jx. And now that would cause it to be impedance match. Keenan, again, thank you.